Okay, welcome back, everybody. So, last lecture we stopped with a discussion of the classical Ramsey numbers. We hadn't discussed them too much yet, just related them to questions phrased in a slightly different way. So, just to remind you, the classical Ramsey number RPQ is the smallest integer n such that every edge to coloring of the complete graph on n vertices either contains an entirely red, so that we're talking about coloring the edges here, complete graph on P vertices, or a completely blue complete graph on Q vertices as a subgraph. Okay, so we saw before that when one of these is 1, this number is just 1. Okay, because having a red or blue K1, this is an easy thing to see as far as the substructure here, because there's no edge to color in the first place. So this is a little bit too small. We related this, and I'm going to return to this in a second, but we related this to the question that I began when I first wrote down the words Ramsey theory here. The question was, how many people are required at a gathering so that there must exist either 3 mutual acquaintances or 3 mutual strangers? And I explained that the answer to this is the classical Ramsey number R33. The reason being that if we think of how to compute this, what would 3 mutual acquaintances or 3 mutual strangers look like? Well, they would look like this. 3 mutual acquaintances would be a red K3. That is, here are 3 people, and we would say that a red edge between them says that they know each other. So 3 vertices arranged in this fashion with red edges in this way. These are 3 mutual acquaintances. 3 with blue edges. Remember, red is the thick here. This is the way that we color and with a single color. Red is thick and blue is thin. So here, 3 people arranged in this way that do not know each other. This would be a blue K3, a blue complete graph on 3 vertices. And so this question then, what's the smallest number of people in such that we're guaranteed either of these things? That is R33. That is exactly this classical Ramsey number. Okay, and this is the one we're going to be very interested in computing, and I'll talk a little bit more about that. But anyway, this is kind of like our motivation here. But before we move directly to that one, let's ask the following, which is what about this one? What about the classical Ramsey number R24? So this is the smallest integer n, such that we either have a red K2, right, complete graph on 2 vertices, or a blue K4, complete graph on 4 vertices. So our claim is that this is 4. Now, if we are going to prove this, what would I need to do? So first, I'm going to show that this is greater than 3. So first, show that this is at least 3. And then the second part, and show that a red K2 or blue K sub 4 is guaranteed in any edge 2 coloring of K sub 4. Because this shows that this is the smallest such number, right? So the first part shows that nothing smaller than 4 will work. And then the second part shows that 4 itself works. So then by definition, the smallest positive integer such that you're guaranteed a red K2 or blue K4 is going to be the 4, right? Or out of an edge 2 coloring of case of n is going to be 4. Okay. So how do I show this first one? So first, I wonder, let's show this. So I don't need to do this for every single case. I just need to do it for the largest case, because if it's true in the largest subcase here, then it's going to be true in the smaller subcases. Right, so what do I need to do to show this? I need to show that in any 2 coloring of case of 3, that in any edge 2 coloring of case of 3, that there is either this is too much. All I need to do is show that an edge covering exists. So I need to show that there exists an edge 2 coloring of K sub 3 for which there is no, I should say such that there is no red K2 nor blue K4. Okay. So I need to show there exists an edge 2 coloring of case of 3 such that there's no red case of 2 nor blue case of 4. Well, here is case of 3. There is obviously no blue case of 4 as a subgraph here because case of 4 would be too big. There's only 3 vertices here, so case of 4 is not going to be a subgraph of this. So that's, I can rule that out. Now I just need no red case of 2. But the way that I've colored this, remember a thin edge is blue, so maybe I'll just write in that I've colored all of these edges blue. That is a valid 2 edge coloring of case of 3. It does not contain a red case of 2. A red case of 2 would just be 2 vertices and the connecting edge that the edge between them is colored red. That is a red K2. That doesn't exist here. So there is no red K2 here, nor is there a blue K4. And so this means that this classical Ramsey number, whatever it is, has to be greater than or equal to 3. Sorry, not equal to, strictly greater than. It can't be 3 because here I've exhibited an edge 2 coloring that does not contain a red K2 nor a blue K4. Okay. Now I have to show that any edge 2 coloring of case of 4 contains either a red K2 or blue K4. If that is the case, then 4 is the smallest such integer that satisfies this, and so since we've shown that there can be no smaller such integer, because this number has to be greater than 3, 4 is going to be exactly what this is. So how do I do this? So for the second part, suppose we have some edge 2 coloring of case 4. If any of the edges are red, we have a red case of 2. Because what does a red case of 2 look like? A red case of 2 is simply this. That's it. So a red case of 2 is that. So a single red edge gives us a red case of 2 as a subgraph. Okay. So if we have a single red edge, we have a red case of 2. So suppose we don't, right? This is the only thing that could obstruct us from having one of these things. So suppose we don't. So suppose no edge is red in this 2 coloring. Then all the edges are blue. And we have a blue case of 4, which is just the graph itself. It's just the case of 4 itself. And the 2 coloring we would have in that instance, where not a single edge is red, is the 2 coloring where every single edge is blue, which is a blue case of 4. And so we've shown that regardless of what is going on here, we either have a red case of 2 or a blue case of 4, which means combining these two means that this classical Ramsey number R24 is 4. Okay. Here's a quick question. You might have already noticed the pattern here, or what kind of argumentation you could use for some other cases here. Question. What about classical Ramsey number R25? What about R217? R251? Just picking random things here. So what is this? It turns out that classical Ramsey number R2k is k for all integers k greater than or equal to 2. Okay, so just like when either P or Q was 1, we got a simple answer for these because, again, the substructure you're looking for is like very small. Here, when one of P or Q is 2, this is also easier to do. Again, the substructure you're looking for is very small here, right? I should say the smallest substructure that shows up is very small. When one of those is 2, you're looking for a blue or red case of 2, but that's like a single edge in its vertices, right? So this is a very simple substructure. Okay, let's keep going. It's not going to be super obvious at first, but let's return to that question. So remember where this came from. Let me bring it back on the page. I asked this question: how many people are required at a gathering so that there must exist either 3 mutual acquaintances or 3 mutual strangers? Another way of phrasing this is what's the smallest number n of people that are required at a gathering so that this must be the case? And I've explained a couple of times now why the classical Ramsey number R33 computes this, and you are looking for the substructures indicated here, right? You're looking for either a red K sub 3 or a blue K sub 3. Okay, and you're looking for the smallest K sub n where one of these things is guaranteed. So we have the following theorem. And this is that R33 is equal to 6. Okay. And so in our proof of this, first step, what is it that I am tasked with here? So just like in the previous case, I want to rule out that there could be a smaller integer where you're guaranteed to always have a blue K3 or a red K3. So I want to make sure that 5 doesn't work here. So then what am I looking for? So first, I show the existence of an edge to coloring of case 5 such that there is neither a red case 3 nor a blue case 3. This will show that whatever this classical Ramsey number is, it has to be strictly greater than 5. Okay. So, here is my first, we're going to draw a case of 5, and then I'm going to indicate the coloring. So we need to connect those. Need to connect those. And we're all good, right? Now we're all degree 4 everywhere. We're good. We're happy. This is K5. Let's do an edge 2 coloring that doesn't give us a red K3 or blue K3. So how do I do this? Well, actually, what if I just color the outside edges red and nothing else red? So everything else is blue. So outside is red, this one is red, all the other, this outside cycle, I color red, everything else is blue here. This is a completely valid edge 2 coloring of case 5. But notice that the way this is done, there is no red case of 3 as a subgraph here, because there's no red case of 3 as a subgraph of that. This cycle that I've colored here is really C sub 5. And among the thin edges, of course, there's also not a case of 3. So there's not a blue case of 3, right? Okay. So that does it, right? No red case of 3, no blue case of 3. Which implies that this Ramsey number, whatever it is, has to be greater than 5. Okay. So now, just as before, I want to show that 6 works. So now I want to show that any edge 2 coloring case of 6 will have either a red k sub 3 or blue k sub 3. This means that this fact is true for n equals 6. Since it is not true for any n less than or equal to 5, that means that the Ramsey number has to be equal to 6 because it's the smallest such. Okay, so I want to show that any edge 2 coloring k sub 6 will have either a red k sub 3 or blue k sub 3. How do I do this? Suppose I have some coloring on k sub 6. So suppose k sub 6 has been arbitrarily edge 2 colored. So it's been 2 colored in some way. Okay, so every single edge is either red or blue. Okay, let V be a vertex of k sub 6. Now we know that the degree of any vertex of k sub 6 is 5. And each of those edges are colored red or blue. So V is either incident with at least 3 edges or at least 3 blue edges, right? So V is incident with either at least 3 red edges or at least 3 blue edges. So think for a second why that is true, right? I mean, it's incident with 5 edges. Those edges can be colored either red or blue. That's it. So in any arrangement, right, the smallest number of red or blue edges is 3, in the sense that if maybe V is not incident with a single red edge, then all of the edges it's incident with will be blue, but that's at least 3, right? So 5 is at least 3. Similarly, maybe it is not incident with a single blue edge. Every edge is red. That would be 5 red edges, but that's at least 3 red edges, right? So there's no possible way of doing this so that V is only incident with, say, 2 red edges and 2 blue edges, because it's incident with 5 edges, and red and blue are the only 2 choices, right? So at least 3 in both cases. So one of those things is true. Okay, I can assume either of these, of course, without loss of generality. So without loss of generality, let's assume that V is incident with at least 3 red edges. So W log, right, without loss of generality, assume V is incident with at least 3 red edges, and call them, we'll say Vx, Vy, and Vz. Okay. All right. Now, these are complete graphs, so these other vertices we have, we know how adjacency works in a complete graph, right? There's like not so many cases here in the sense that we know exactly how these things are related by adjacency. So the next question is, what about the colors of the edges like xy, xz, yz? All right, so And this coloring that we fixed, what about the colors of x, y, x, z, and y, z? So let's draw like the picture here, right? So K6 is not so big that I can't draw how this goes. So here's my 6 vertices. Whatever I have called them, let's say that V is this one, right? And the vertices x, y, and z that I've picked out look like this. Okay, we'll say this is x, y, and z. This is how we've labeled them. Okay. But the question is, what about the colors of x, y? I'm going to draw it with a dashed line. X, z, and y, z. So remember, I assumed at this step that without loss of generality, I assumed that V is incident with at least 3 red edges, and we've given names to all these edges. So all of these are red, even though I haven't made this fat, right? So because I didn't want to make the picture uglier. So we'll say that all these are red edges. Maybe I can even draw that in. Red, red, and red here. Okay, so all those are red. Now, here's the thing, right? For these edges, if none of them are red, then all of them would be blue, and this subgraph here is a blue K3, right? So if none are red, then they're all blue, which gives us a blue K sub 3. It would be this triangle, this dashed line triangle that I've drawn in here. Every single edge would be blue. We would have a blue K sub 3, and we'd be done since we would have one of these things. All right. If at least one is red, then we have a red K sub 3. To see this, what if this one is the red one? Well, then this subgraph is a red K3. What if this one is the red one? Then this subgraph is the red K3. What if this one is the red one? Then this subgraph is the red K3. So in either case, we either have a blue K3 or red K3. And so any two coloring of K sub 6 produces either a red K3 or blue K3, which means our Ramsey number is equal to 6 because, again, we already showed that it had to be greater than 5, and we showed that it works for 6. Thus, 6 is the smallest such integer, so this classical Ramsey number is equal to 6. Okay, so R33 is equal to 6. This is the statement that you have to the smallest number of people at a gathering to guarantee either 3 mutual friends or 3 mutual strangers is 6. You need 6 people to absolutely guarantee it. Okay. So similarly, it can be argued. The next theorem, R34 is equal to 9. So here, the proof, this is on page 119, but I want you to know this uses both that R24 is equal to 4 and that R33 is equal to 6. So if you had questions that, oh, is there some kind of like either recursion relation or some kind of way in which these Ramsey numbers build out, they're used, well, you can, of course, kind of see how some of this arises, but this isn't going to be like as helpful as you might think. Here, it's not going to be super helpful in the completely general case, but it does help in this case. So I'm not going to do this proof, but you can have a read over it. It's pretty short. It's similar in spirit to the proof we just did for R through 3. And so the question then is the following, which is what are some known Ramsey numbers? So we did R 1K is always 1. R 2K is K. R 3 is equal to 6. R 3 is equal to 9. Turns out that R 3 is equal to 14. R 3 is equal to 18. R 3 is 23. Again, there's symmetry between the arguments, so these, the same thing is true if I'd replace 7 and 3 here. R 3 is 28. R 3 is 36. R 4 is 18. R 4 is 25. You may be under the impression at this point that I can keep going, and maybe you're trying to rack your brain looking for some kind of closed form expression that generates these, or you're trying to see a pattern here, but don't worry. Save your brain power because it turns out this is the full list, as in these are all known Ramsey numbers. These are the only Ramsey numbers known. So, for instance, i.e., R55, this is an open problem. R66, very open problem in the sense that this is substantially harder than even this. These are open problems. There are some bounds. There are some specific bounds. So there are some bounds known. For instance, whatever R46 is, it is known to be between 35 and 41. R55 is known to be between 43 and This bound says 49. This was improved last year to 46. So, in fact, this is known, like I said, this is like cutting edge research. Got this down to 46. This is from 2024. I don't know the author's name off the top of my head. Actually, let's go ahead and look that up. No reason to, it'll take me like 10 seconds. Let's see here. Engeldveit and McKay, 2024. So this is 2024. Engeldveit and McKay. So this is very new. This bound, like I said, the previous bound before that was 49 here. R56. Which is bound between, let's see, 58 and 87. And R66 is bounded between 102 and 165. Now, this might come as a shock to you just because you're probably thinking in your head, okay, wait a minute, like this might seem naively as something that would be very amenable to just some kind of brute force computation, maybe, and you know like what sorts of computations, like say a modern cutting edge GPU can handle, especially if you got a bunch of them linked together, right? So you may say, why isn't this something that computation hasn't already knocked out? It's not quite so simple. It's much harder than that, and it's well beyond the brute forcing. This is not the play here. It's well beyond the abilities of computers to handle this. Even right now, like it's not like in the last couple of years they've cleared all these up. No, there hasn't been that much progress in computing these things. So this is kind of a warning here. Going to read a quick quote from Paul Erdős, famous mathematician I've mentioned before when we talked about Erdős numbers, because he'd published so many papers. You could think of the Erdős graph of adjacency relation between someone and Paul Erdős as they published a paper with him, and then other adjacency relations is publishing a paper with someone who published a paper with Paul Erdős. You know, that's adjacency is publishing papers here. So this is, you know, the Bacon graph or the Erdős graph. Anyway, Paul Erdős, who worked on these Ramsey theory problems and classical Ramsey theory stuff, said the following. Suppose an evil alien would tell mankind, either you tell me the value of R55 or I will exterminate the human race. It would be best in this case to try to compute it both by mathematics and with a computer. But if the alien instead asked for the value of R66, the best thing to do would be to kill him, because you're not going to be able to do it. Humanity is not going to be able to compute this number to appease the alien overlord, so you better just kill him, because it's not happening otherwise. So this is just a way of kind of illustrating that this is tricky. This is very tricky. And even when you keep the numbers in question relatively small, pondering what is going on when you ask a question like this is a lot more interesting than it might seem at first. Okay. The notion, of course, of Ramsey theory has kind of expanded to mean asking these kinds of questions, not just about these classical Ramsey numbers, but or this specific structure, but basically asking a question about how much of the structure has to exist, what's the minimum amount of structure that has to exist for some other substructures to arise. In a vague sense, that is what we're asking with the classical Ramsey theory stuff, but you could generalize this more so that maybe the structure you're looking at is different, or maybe the substructures you're looking at are different. So I'm going to see one generalization of that, but I'm going to state a few things here. So I'm going to state a few facts. So here are some random facts about classical Ramsey numbers. So this is going to be just a list of theorems. I'm not going to prove any of these. So for positive integers p and q, the Ramsey number RPQ is less than or equal to p plus q minus 2 factorial over p minus 1 factorial times q minus 1 factorial. The thing that you were curious about when I did the example of like R24 and then R33, and I mentioned that in the proof of that R34 is 9, that proof uses the fact that previous Ramsey numbers were known to us. Here is a theorem that relates, gives a bound for RPQ based on previous Ramsey numbers. Of course, there's 2 slots here, so it's hard to say what previous means, but you'll see what the theorem says. If P is greater than or equal to 2, Q is greater than or equal to 2, then RPQ is less than or equal to R P minus 1Q plus R P Q minus 1. So this is the sense in which we mean this relation behaves in this way. Okay. Furthermore, if both terms on the right of this inequality are even, then the inequality is strict. So furthermore, if both terms on the right of this inequality are even, so if both terms on the right-hand side are even, this inequality is strict. You see that this is an important thing when the sorts of bounds we have are like this, right, where there's not a huge window here. So improving an inequality by passing from a non-strict inequality to a strict one is actually doing some work here. You're effectively narrowing the window ever so slightly, and there's not that many more steps to go, right? Maybe this is a hope you might have for computing some of these other Ramsey numbers, is there's bounds and bounds and bounds more and more, and you're like trying to toss out one case at a time until you get down to only one thing it can possibly be. So here's another theorem. So this is for the special case that you have. You might have noticed the pattern we were going for here when we wrote all classical Ramsey numbers. Here we did the case where one of them is 1, the case where one of them is 2, but when one of them is 3, get a bunch of different things, and then we just kind of stopped, right? Like R310, what is that? And so on. So the question is there any kind of thing I can hope for here in the case that, say, P is 3? So for every positive integer Q greater than or equal to 3, our 3Q is less than or equal to Q squared plus 3 over 2. Okay. One more. This theorem is due to Erdos himself. This is the case when P and Q are equal. So if P is greater than or equal to 3, then classical Ramsey number RPP is strictly greater than the floor function 2 of 2 to the n over 2, where this is the floor function, right? Where this is the greatest integer less than or equal to x. Okay. So there's a number of results on these things. Again, there's an outgrowth of this because these classical Ramsey numbers obviously are very hard to compute. Like here is the entire list of all of them. If you compute more than is on this list, you're going to be doing essentially uncharted territory stuff. This is, you know, that might be worth a PhD if you can figure out how to compute new classical Ramsey numbers. That would be a pretty big deal. That would make you pretty happy in terms of your mathematical achievement. So anyway, I had mentioned that we might think of generalizing this to not talk about specifically these substructures, but be a little bit more general with the substructures we're talking about. The natural generalization is to replace seeking copies of a red case of P or blue case of Q with seeking different subgraphs, not necessarily just complete graphs. So this leads us to what's called Graph Ramsey theory. There are other examples of applications of what could be called Ramsey theory to other contexts, to other settings, but this is one that is very suitable generalization for us. You might say, wait, we can't even do the classical stuff, so why are we generalizing? Isn't that just going to make our life harder? Well, some of the questions might be harder, but others might be easier. And also, because it's different enough, but if it's a generalization in the right way, maybe you can see something in the generalization and then push that back down to the specific case. That's always the hope with this. How often does that happen, that you get a satisfactory answer in that way? Well, I don't know the exact numbers on that. It has happened before in math. This is a frequent tool that is useful, but does it always help, or does it just add more questions to be answered? I'll leave that up to you as you're going through your studies with this stuff. So what is the idea here? So what is Graph Ramsey theory? So given graphs G and H, the Graph Ramsey number we'll call it RGH, is the smallest integer in such that any edge to coloring of case of n contains either a red copy of G or a blue copy of H. Okay. So, obviously, if G is K sub P and H is K sub Q, then the Graph Ramsey number RGH is just equal to this, which is the classical Ramsey number RPQ. Right, so this is definitely a generalization. It's just that instead of always looking for copies of a red K sub P or a blue K sub Q, I could look for generic graphs. These graphs, G and H, could be trees, for instance. Right? They could be trees. They could be some other type of subgraph. They could be, any sort of subgraph here, potential subgraph K sub n that you want. So this is definitely a generalization. We have the following that we can actually prove very quickly. So if G is a graph of order P, H a graph of order Q, then the Graph Ramsey number RGH is less than or equal to the classical Ramsey number RPQ. Okay, quick proof. Let n be whatever the classical Ramsey number RPQ is, and consider an arbitrary, so just any edge 2 coloring of K sub n. By definition, K sub n contains either a red KP or blue KQ. So by definition of the classical Ramsey number, K sub n contains either a red K sub P or blue K sub Q. But G is a graph of order P, H is a graph of order Q. So both of those are subgraphs of the complete graphs on P and Q vertices respectively. So since G is contained, because think about what the complete graph is, right? The complete graph is all the vertices and all the edges, right? So it is, you throw in all the vertices of that order, so like exactly like in the case of n, you have n vertices, and then you throw in every edge that could possibly exist between all of them, right? You have the maximum number of edges, like nothing is left out, right? So necessarily G and H have to be subgraphs of those. So G is subgraph of K sub P, and H is subgraph of K sub Q. Then there must be either a red G or blue H, because if there's a red K sub P, every edge of this K sub P is red. If G is subgraph of this, every edge of the G here is going to be red. Every edge of the blue here, or every edge of the H here is going to be blue. So there is either a red G or blue H, right, in K sub n. Thus, whatever this graph Ramsey number is, at most it can be this n. But this n is exactly the classical Ramsey number. Okay. So that is how this works. I'm going to present a few other results here. So one, it is that the Graph Ramsey number RGH is greater than or equal to the chromatic number of G minus 1 times what I'm going to call C of H minus 1 plus 1, where C of H is equal to the largest component of H. It's the order of the largest component of H. Okay. So the proof of this theorem is a result of Jvatal and Harari. I'm going to, it's a short proof. I'm not going to write out the whole thing. I'm just going to show you a picture. So this picture explains the idea. The idea is to consider the graph S formed by taking m copies of K sub n and adding all of the edges between each copy. So talk about a maximal graph, right? You take a bunch of copies of K sub n, these complete graphs, and then in between them you add in all of the edges between each copy. Okay. So you can see that this actually is the complete graph on mn vertices. If you've taken m copies of these, this is a complete graph on mn vertices, and that's basically the main part of the proof. So this is the thing that allows you to say what you want to say about this and brings in the order of the largest connected component of H and the chromatic number. Okay, but I'll leave that to you. More facts here. Let's do another. I had mentioned what if like one of these is a tree, right? If T sub m is a tree with m vertices, then what is the Graph Ramsey number of tree with m vertices and K sub n? This is actually m minus 1 times n minus 1 plus 1. So here's an example where this generalization actually led us to an answer, because the substructure we're looking at here is a tree, which is simpler, right, than one of these complete graphs. Okay. So again, I'm not going to go through this proof. This is on page 125. But you can have a look at that. This is actually, both of these are examples of proofs that we can do in this class. This doesn't involve anything extra coming from outside. These are two proofs that we can understand. we have another one involving two specific classes of graphs. So one is a tree, one's a complete bipartite graph. So here's another theorem. If T sub m is a tree of order m, and if m minus 1 divides n minus 1, then if it divides n minus 1, then n minus 1 is an integer multiple of n minus 1 and times some integer. So then this Graph Ramsey number of the tree with m vertices and the complete bipartite graph having partite sets of size 1 and n is m plus n minus 1. Again, very nice answer in the case that one of these substructures we're looking for is a tree. Okay. Similarly, if mk1 denotes the graph consisting of m copies of mk1, is the graph consisting of m copies of k1, then we have the following theorem, where if m is greater than or equal to n, which is greater than or equal to 1, then the Graph Ramsey number of m k2 n k2. I should have, why did I use k1 here? I should have used k2 here, yeah. There. So this is mk2 and nk2. This is 2m plus n minus 1 is this Graph Ramsey number. So some questions you might have. We had some answers in these theorems for specific classes of graphs. So, for instance, what is the the Graph Ramsey number where the thing you're looking for is a path on 3 vertices? This is the substructure here now, right? What about the cycle C sub 4? What about Graph Ramsey number P sub 3 C sub 4? Well, you can have a go at some of these things. Maybe you'll be asked to do this shortly on some problem. But remember what it is you're actually doing here. Now, while we saw that we got answers in very specific classes of graphs, doing this in general is obviously hard. We know that just because even if we restrict to the case where G is K sub P and H is K sub Q, that's the classical Ramsey numbers, which are extremely hard to compute. So this shouldn't be that surprising that this generalization leads to numbers that are also very hard to compute. But hey, we get some nice results out of this otherwise. So that's that is more or less all I wanted to say about Ramsey theory for now. There's a lot of interesting questions, of course. I could keep going here with the interesting uh, uh, directions, but any more than this we would have to get very lost in the weeds to say more. So I'm going to stop here. Of course, if you're interested in any of this stuff, specifically like Ramsey theory and stuff, I can tell you which books you could take a look at, which things you could investigate to go kind of on the next logical path here. And that's true not just of the Ramsey theory stuff, any of this graph theory stuff that we've been doing, whatever. If you're interested in any particular topic, you can let me know. There's not that many of you, so just email me and let me know, which of these things you're most interested in. I can give you some reference that is, since right now we're doing essentially like the undergrad or advanced undergrad treatment of this topic. Anything else? There are some advanced undergrad level stuff, but going further, you're going to probably be looking at graduate level textbooks, which is perfectly fine. But that's what happens, right? When you go far enough in a subject, you're getting to the point where you're doing graduate level stuff. That's good, right? That means you're progressing in your knowledge, so it's a good thing, not a bad thing. That the only place to go from here is up, 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 further, further along, further down, or if you want to view it as up, maybe if you're being positive, you want to view it as down, a descent into madness or something, and you can view it like that as well. So either way, whatever makes you happiest to view it as. But that's how it's got to be, just because these things are complicated. So anyway, that's basically all I wanted to say about Ramsey theory, which really tidies up kind of all of our graph theory treatment. Some of it, of course, is going to come back. Obviously, the stuff we were doing near the end had a lot of combinatorial flavor. But now this brings us on from graph theory to combinatorics. Again, I shouldn't even say like on from graph theory in the sense that we're not returning to it. All these things are very connected. You've already seen that when we get into this desire to count some quantities in graph, then we are doing combinatorics. These things are obviously intertwined. You may have heard of various you might have heard of, say, enumerative combinatorics. Um, which is technically counting, right? This is the mathematics of counting. Maybe this is kind of the only way you have experienced combinatorics, although probably not. You have probably seen some other sorts of ideas here. There's what you might call existential combinatorics, which might not have to do strictly with counting, or might have to do with the existence of arrangements that possess some specified property. So existence of arrangements having specified properties. Of course, maybe you are interested in the number of such arrangements, so you would be counting these things as well. So I'm not saying that these are disjoint fields of combinatorics. Obviously, there's going to be plenty of overlap here. There's what might be considered like constructive combinatorics, which is the design and study of algorithms for creating arrangements with special properties. So design and study of algorithms for creating arrangements having special properties. We'll say specified properties. I'm not even going to write it down, but you could say like algebraic combinatorics, for instance. I remember that was actually the title of a course I took when I was a grad student at UMD. It's not always offered. It's usually a topics course. Not sure the last time it was offered, but it had to do with actually, do I have the textbook over here on my shelf? Oh, I do. Hold on for a second. Let's pull something off the shelf. Boom. We got this is the textbook that was mostly used for that course that I took. This was a graduate course in what was called algebraic combinatorics, which had to do with, as you see, the name is Young tableau. What is a Young tableau? I'm going to come up with some examples where we actually refer to tableau, but basically here, Young tableau are objects like this. There are these tableau box arrangements that can be filled with numbers satisfying certain rules, and I'm not going to get into that right now. But what might I say? So these, yeah, you have Schur polynomials. This is kind of like one of the key, like, central properties. Here's some more examples of Young tableau. Like I said, I'm not gonna. You can look up the rules that these satisfy, but what I'll do instead is give you kind of the application of these things, or one application of these things. It's like suppose you have an election that has some number of candidates, right? And a final vote tally would correspond to numbers assigned to some number of numbers assigned to each candidate, and we'll say that this has 100% turnout, right? So every single person votes. So basically, the number of voters is equal to the number of potential voters, the number of registered voters. So anyway, it's an assignment of some number that sums to the, among all candidates, would sum to the total number of registered voters of some numbers, right? Which is how many votes they got. When you start asking questions, though, about the number of different voting arrangements of the candidates for that number of voters, when you start digging into a question like that, you'll realize that that's a very hard question. When you ask things like, yeah, what are the number of different orderings on the candidates? Not just here's a list of candidates, how many orderings. That's a much easier question. That's something you could already do, right? You have to do that in basic probability. You need enough counting to deal with that. But if I ask you, like, basically the number of different ways in which you could run a vote and get the same vote order of the candidates. Say there's like 20 candidates, right? It's like the number of different ways voting could happen to keep the order the same, the number of different ways the voting could happen to swap the top two candidates. It's like you actually start thinking about that. Those might be hard numbers to get your hands on. And yet these Young tableau are, an object constructed to help answer that sort of question. So that's the sort of thing that creeps in here, that it has overlap with all of these things. So these are not disjoint or anything. All these are related, but these are some words you might hear thrown around. So let's just go down the list here, and I'm just going to read a list of essential, like, some basic combinatorial problems. Should a straight beat a flush in a game of poker? What about a full house? What am I implying here? In a game of poker, it would make the most sense for the rarer hand to be worth more in terms of winning. So the hand that is more rare to achieve should beat the hand that is more common, right? So that is a way of determining like how to set what hands beat what other hands in a card game, for instance, like poker. But then necessarily this is involving probability straight off, right off the bat. You're talking about probability because you are counting the total number of arrangements where this is what you end up with, and seeing how that relates to the total number of arrangements where you don't care, right? That gives you a probability. If you're assuming, the deck is well shuffled and all this, and it's if you're assuming equal probabilities in the underlying events that you're talking about, the underlying outcomes you're talking about, and that is a frequent assumption when you're doing this like finite probability stuff, then this is a probability. This is a question about probabilities, but necessarily that makes it about counting for these finite sets, as we'll see. Suppose a lazy professor collects a quiz from each student in a class, then shuffles the papers and redistributes them randomly to the class for grading. How likely is it that no one receives his or her own quiz to grade? Again, right off the bat, this is a probability question, but necessarily that means it is a counting question. In this, again, this is a finite thing where you have some number of students in a class, so there's some number of quizzes here. There's all finite numbers here, so we can actually count these things and figure out what is the likelihood of this happening. How many ways are there to make change for $1? That's a question that you could ask, right? How many different necklaces with 20 beads can be made using rhodonite, rose quartz, and lapis lazuli beads if a necklace can be worn in any orientation? Okay. How many seating arrangements are possible for N guests attending a wedding reception in a banquet room with K round tables? Okay. Suppose 100 medical students rank 100 positions for residencies at hospitals in order of preference, and the hospitals rank the students in order of preference. Is there a way to assign the students to hospitals in such a way that no student and hospital prefer each other to their assignment? Is there an efficient algorithm for finding such a matching? Again, you start to see immediately the sorts of applications here and why this might be good and interesting and important. Is it possible to find a collection of n greater than or equal to 3 points in the plane, not all in the same line, so that every line that passes through 2 of the points in fact passes through a third? Or if we require instead that no 3 points lie on the same line, can we arrange a large number of points so that no subset of them forms the vertices of a convex octagon? That one, you're going to have to draw some pictures there. You might not have the intuition there to see what it is that's going on. But nevertheless, all of these are examples of the wide variety of combinatorial problems that you can cook up. Not all of these totally divorced from, say, the graph theory questions that we've asked. We've already seen that it has shown up in graph theory for us. And so I am going to say a couple things that basically are tell us the important things, and then I'm going to finish for today, and we're going to keep going tomorrow. So first, like the two maybe like classic counting rules. And it's these two things from which all of the counting that is subsequently done arises from. So here's the sum rule. If S1, S2, and so on up to, we'll say, S sub m are mutually disjoint finite sets, and the cardinality of S sub I is equal to n sub I for all I between 1 and m. Then the number of ways to select one object from any of the sets is the sum of the number of possibilities for each set. Of course, this may just seem like obvious on its face to you, but we write this out because a lot of what you are doing when you are skipping steps in your head and doing these counts, you're using this. Similarly, the one that really you see and you feel being used often in these. This is when you are making a selection in sequence rather than a single selection. So again, suppose S1, S2, and so on, up to Sm are finite sets. And they have size that is cardinality n sub I for each I. Then the number of ways to select one element from S1 and then one element from S2, so followed by one element from S sub 2, so on, all the way out to one element from S sub n, is the product n sub 1 times n sub 2 times n sub 3, and so on, out to n sub m, provided that the selections are independent. Which means that the elements chosen, i.e., the elements chosen from S sub 1, S sub 2, and so on, up to S sub I minus 1, have no impact on the element chosen from S sub I. And that's true for all I. This product rule is, of course, typically like the first thing that is written down on the board when you are doing basic combinatorics in like a probability class. So in probability class, when you're ready to like start counting at the very beginning, when you're doing basic probability stuff, this is like the first tool in your arsenal, basically, right? Is this product rule, right? These two things taken together, these are the very, very basic methods of counting, and yet this is where it starts, and this is everything that we're going to talk about essentially stems from these. So we just get more and more sophisticated with how we can treat these things. We see the same patterns arising, so we know what to do. But ultimately, these two things are basically where all of the counting comes from. Okay, so I think it's a good stopping point here. We'll continue on with this combinatorial stuff. We are, like I said, we're full blown into combinatorics now. We're going all the way. So we're not returned to graph theory until it's time for some applications of this combinatorial stuff to 2 questions in graph theory, other than the ones we've already seen. So we are moving on to combinatoric stuff. I will post your exam later today, and I'll send out an announcement on Elms when I do that. So be looking for that. But you don't have to sit there refreshing Elms constantly. You're going to have a few days to do it, so just relax and wait for wait for the announcement. You'll have plenty of time to work on it. So anyway, it'll be same format of the homeworks. You're not allowed to work with any other students or anything though. So no collaborating with other students. It's all you. And that would be that. So anyway, I will post the exam like I said later today. So and I'll send out an announcement when I do. Anyway, so I will see you all tomorrow where we'll continue on with this combinatorics stuff.